Okay, so next topic by Andrea Ferretti, who's a senior researcher at CNR in Modena and Reggio Emilia, and he's also chair of the Max Center for the Transition to Exascale. So Andrea, the floor is yours.
Thanks, Matteo, for the introduction. So this talk is a follow-up on Ismaila's presentation on some specific aspects. So here we will dig into the details of some aspects of the Koopmans functions, in particular their connection with a sort of a functional theory of a spectral density. So how can we use and why, more importantly, Koopmans functions to predict spectroscopic properties. So here is the outline of the talk. I'll provide a summary of Koopmans compliance functions, just for the sake of completeness, and then I'll provide some assessment about molecules, both ionization potentials, that if you want are ground state quantities, but also spectroscopic aspects, and then I'll try to draw a connection about theoretical framework where the Koopmans functional may be thought to live in. So we've already okay. So we've already heard that. So that, yeah. The exact total energy in DFT should be piecewise linear, and instead the observation is actually that approximate energy functionals instead are not. In particular, we have convexity for local and semi-local approximation, and concavity, if you want, for R3 Fock and hybrids with a large fraction of the exchange, and via Janak's theorem, somehow this turns into a dependency of eigenvalues on their own occupation. In principle, this is exact in DFT just for the topmost eigenvalue. So we just can say that due to this convexity, it's the HOMO eigenvalue that depends on its own occupation. But in the reasoning, what we are doing is that in order to correct this, we apply a linearization to all eigenvalues as a function of their occupation. And this is a crucial aspect, is a part of the construction of Koopmans. In order to be able to correct, we do this. And also let me remind that this is tightly connected to the DFT plus U construction. So a similar picture we have seen from the very first days connected to Coccoccioni and the Gironcoli view on DFT plus U, and it's really restoring piecewise linearity. Okay, so actually over the years we passed from mentioning self-interaction to really restoring piecewise linearity, and that is also something that is there in the literature. So self-interaction has been defined in several ways. There's one electron exactness of method, but then also Perdue and Wei-Tao-Yang separately defined the many-body self-interaction really related to piecewise linearity. And the reason is exactly this, because via Janak's theorem, that is not just a property of DFT, Janak's theorem you really hope to have in many of the theoretical framework you deal with, and is actually there, is really tightly connected to variationality in a sense. You really would like this derivative not to depend on its own occupation. Again, piecewise linearity. And these are the concepts that we have been using to assess and address energy levels as out of direct and inverse photoemission spectrum. Here is where the development of Koopmans compliant function actually linked. Some of the references already mentioned. And in a nutshell, what you do formally within Koopmans, you realize that in your DFT functional, you have this piece of the energy that just comes, is just the integration of Janak's theorem that gives you this amount of energy that depends on is what gives convexity. And we just want to substitute this amount of energy with something that is linear times a constant that has to be determined. So if we do this, somehow we are taking out what we don't like, we are re-adding what we like. So we are taking out the convexity and re-adding something that is piecewise linear. Still, this has to be determined, and not just determined randomly, but we want to determine that with accuracy. And we know that if this has the shape of an eigenvalue, that this second or finite difference approximation here, that is the difference in total energies between n and n-1, typically is a good approximation to what ionization energies are at variance with eigenvalues instead that are derivatives. So somehow we are here trading derivatives with the finite differences for exact function that you should be identical. In approximate they are not, and they split, and we choose the one that is more accurate, if you want, that is the finite difference. So that is one option. And in principle, you can estimate that either with the derivative at half distance or actually taking the total energy differences as here. And this already introduces an important concept, that is that the Koopmans construction comes in different flavors. So there are several options, and you can consider that we already had a discussion about the Ki functions that has some properties, and there are actually more than these two. In particular, we cannot just start from a DFT functional, but we can already provide in the DFT functional some self-interaction corrections like Perdue-Zunger that is meant to correct for one electron exactness. And so we can come up with the KI-PZ function that in terms of accuracy is probably the champion of the set, in a sense. So it's one always among the most accurate. So in doing all of this, somehow all the reasoning has been done just looking at the dependency on occupations, let's say in a frozen orbital picture, and that is somehow reminiscent of the Hartree-Fock Koopmans theorem, where you work out everything keeping orbitals frozen, but then of course while doing these ionizations you really need to take into account the fact that orbitals do relax, and that turns out to be a screening coefficient that at first was computed by considering that the HOMO with n particles should be identical to the LUMO with n-1. It's really this piecewise linearity condition, but then, and that was key with the work of Nicola Colonna, this was cast into a linear response property, and that can now be computed with the response. Again, I'm pretty sure that you appreciate the similarity with the situation in DFT plus U. At first, you had supercells with changing the potential to evaluate the response U, and then you can do it with linear response. So it's pretty parallel. And as we have seen in Ismail's talk, actually, when you put all of this together, it works. This is so it does what it is meant to do. That is, we look at the topmost eigenvalue of methane as a function of its own occupation. In principle, in LDA, it would be pretty much linear. And then if you do a unscreened correction, this orange, you overdo the correction, as if you were doing Hartree-Fock actually. And then when you include screening, you have this red curve where more or less you are doing a better job. Okay, in all of this, this is just the presentation in a nutshell, but there are some important technical details. First of all, the method just depends on orbital density. So if you want, this belongs to a class of methods that is called ODD, orbital density dependent. Perdue-Zunger self-interaction correction is another example. And being dependent on the orbital density and not on the whole density, that makes the method not unitarily invariant, meaning that if you rotate your manifold, the orbitals in your manifold, of course, your single orbitals change, and the energy in principle changes. So because of this, when you minimize the total energy, you also get a unitary rotation among the occupied orbitals. So somehow you minimize and linearize at the same point. It's not trivial that the unitary rotation you end up with is a localizing rotation. In principle, that could be also anything else. It happens that with the functional we are working with, instead it's typically the case that variational orbitals, so the orbitals you plug in the total energy, gets localized in this form. And then this is the Euler-Lagrange problem for the minimization. At the minimum, you have the so-called Peterson condition that applies on this lambda matrix that makes this lambda matrix Hermitian. During minimization, that is not Hermitian. At the minimum, it's Hermitian. And every time you have an Hermitian matrix, of course, you want to diagonalize it. And once you diagonalize it, you obtain the so-called canonical orbitals. So this is an important point. With orbital density dependent functions, you have two sets of orbitals, those that minimize the functional. And then once you're at the minimum, you can simply rotate them, diagonalizing this matrix, and obtain those that are eigenvector like. In doing this, here, as also Ismaila mentioned, this Hamiltonian is now depending on the orbital. So this is just the derivative of the energy with respect to each orbital density. You get a potential, corrective potential that is orbital dependent. You have one Hamiltonian, different Hamiltonian for each of a local though. And if you want, this is one of the advantages with respect to hybrids. In hybrids, you have a non-local potential that in principle means a different, it applies differently to each of the orbitals, but that's fully non-local. Here we have several local ones. So also computational-wise, that is important. Okay, this slide is just there to say that we are not alone. There are a number, and I would say a large amount of similar developments in the literature. So somehow these developments resonate with all the developments in hybrids, short range, range separated hybrids, and also the electric dependent hybrids. As I mentioned, we have a response, a screening coefficient in front of our corrections, and they build pretty much on the concept of many-body self-interaction freedom, Wei-Tao-Yang and John Perdue, in order to connect the self-interaction freedom, asymptotics of the potential, and piecewise linearity. I think there is this nice review by Kronig and Kummel. And then there are these other methods here that are very similar to some of the flavors of our Koopmans development. This transition state method is very similar to KI, and Sample DFT is also very similar to KI. And then these other two recent approaches by Lin-Wan Wang and Wei-Tao-Yang are also somehow similar to Koopmans functional. So this just to give credits and set the stage. And let's see how it works. So just on molecules, I think later on, Nicole and Edward probably mostly will discuss also solids. And since the GW100 set has become quite popular in the GW community. It's 100 molecules where you look at ionization potential electron affinities. I think Nicola applied this also with different flavors of the Koopmans functional. Here you see Ki, perturbative KIPZ and KIPZ. And as you see, basically, this method works very well. They are among the best methods compared to GW. Also, GW in some advanced fashion. So this is fully self-consistent GW, fully self-consistent, and this is quasi-particle self-consistent GW. So that is, besides vertex correction, somehow state-of-the-art GW, and you see Koopmans does pretty much comparable. Personally, I think that one of the reasons is that Koopmans can be run self-consistently. That is that it's true also these are self-consistent. You see here, these are the best methods, while G0, W0 is down here. I think that is one clear advantage with respect to perturbative method. And similar results have been obtained for the G2, the Gaussian 2 set early on. And so if that was for ionization potentials and also electron affinities, we can also look at deeper states. In principle, as far as ionization potentials are concerned, that is just purely within DFT. So probably not Connaught any longer, since we have multiple potentials, but still within DFT. While here we are really looking at deeper states that are excitation, charge excitation states. And here we are comparing the density of states obtained with Koopmans green with the photoemission signal. And as you can see here, there is no alignment. Here, be careful. In the literature, very often when people do like that, they align the ionization potential. They align the HOMO photoemission with calculations. Here, there is no alignment. So this just comes out of the calculation. Here is where LDA would sit, and similar for there. So you see, it does a very good job also for deeper states. So that is interesting. And if that were density of states, in principle, we can also aim at a better description of the photoemission process. So we can also include some matrix element of the process in this final state plane wave approximation. So that is the simplest approach. And so now these are photocurrents is the photoemission signal. Just look at the top two curves. This is the experiment, and this is KIPZ. You see, when also estimating the photoemission signal, we are still doing a good job here. And with that development, you can also get some extra understanding, that is the dependency on the photon energy of the photoemission signal. In particular, here, photoemission was taken with two photons, and you see that the relative amplitude of the first peaks is actually changed in the experiment. Here, they are more or less the same, and here they are and here not, and we reproduce that, and also this is the plane dependence on the photoemission. So far, in a sense, so good. But then the point is why. So, and we need to try to understand. So it's there is some physical and chemical understanding behind this, but we also would like to build a consistent theoretical framework. And let me here summarize the phenomenology of the theoretical framework we are using. Orbital density dependent, so dependence on each separate orbital density. When I take the derivative of the total energy with respect to each density, I get a potential that depends on each orbital. This translates in this Euler-Lagrange equations. This matrix becomes Hermitian at the minimum, and when I diagonalize, I obtain an expression like this. These are the canonical orbitals, so those that we are used to, the eigenvector-like orbitals, and they have they are subject to a potential that is local and orbital dependent. And this was at first, in the context of the Perdue-Unger case, also seen as a drawback of the method. In principle, that is what would take you out of the FT Konesham. It would be still seen as the FT, but not Konesham. And then Korthdorfer and co-workers have developed OEP, optimized effective potential techniques, to bring that back into the Konesham framework. In principle, you could minimize that subject to the condition of having a single potential, as it's done for the regular OEP. This ODD is slightly different, they call it generalized, but in principle, that's feasible. But the question, if you want, is this typically you don't want to do because it's expensive. And the question is there any advantage? So is there any reason and any advantage in working within this orbital dependent framework? Also, Tommaso's question before related to why Ki is not changing the total energy while changing the eigenvalues, I think can be seen from the point of view of a theoretical framework. So somehow these theoretical frameworks here are more general, and it's not granted that you change the piecewise linearity, that is, you change the eigenvalues, that translates into a change in the total energy may not be granted. And the reason is that you have a framework that is more general than Konesham. So here is the reasoning. We ended up with orbital dependent potentials, and somehow orbital dependent potentials are reminiscent of Green's function theory method within the quasi-particle approximation. That is a situation where we find orbital dependent potentials, and they develop like this. You have a self-energy that is frequency dependent. This is your quasi-particle equation involving the self-energy, this non-linear eigenvalue problem we have seen also yesterday with Tommaso. You do a quasi-particle approximation, you just focus on the poles of the Green's function, and you get an equation like this, where each eigenvector has its own potential. So it is orbital dependent. Orbital dependent because of the frequency, still also non-local and in principle non-Hermitian. But this extra complexity of non-hermiticity and non-locality is actually not strictly needed in the quasi-particle, in the Green's function method, if you want just to describe the spectral density. And this is a paper I personally like a lot. This paper from Matteo Gatti and Lucia Reining from 2007, where they just show and stress the fact that instead of a non-local dynamical potential, you can just work with a local dynamical potential if you want to describe the local spectral density. And then it's immediately clear that if you do a quasi-particle approximation, or if you just focus on the relevant energies, you have potentials that become local and orbital dependent. That is exactly what we get out of the Konesham, out of the Koopmans theoretical framework. And here is the connection. So somehow we can say that the Koopmans theoretical framework in the ORBD fashion is able to accommodate for such spectral function construction, where we've made a quasi-particle approximation. I'll comment better on this in a second. So here we have potentials that are local and orbital dependent, and these are an approximation to the spectral function, or the spectral potential, that is a potential aimed at describing the spectral function of an interacting system. Okay, so our theoretical frame is able to carry approximations to this theoretical framework here. So somehow, if you work within ODDs, it's not granted because it depends on your functional. Your functional could be bad, and you simply won't be describing this, or your functional could be aimed at describing something else. So that would just come by chance. But you can cast these capabilities into your orbital dependent functional. And let me also remark here, since we mentioned a lot Koopmans, that we all at school have seen Koopmans as an approximate property of the Hartree-Fock method, that is an approximate method. So somehow frozen orbital, Hartree-Fock, the Koopmans theorem is valid. And the Koopmans theorem there says that the eigenvalues, the Hartree-Fock eigenvalues, are total energy differences. And indeed, it is little stress, but this is instead an exact property of the exact Green's function. And I think this is very remarkable. So in the exact Green function, in the lemma representation, the poles of the Green's functions that play the role of the eigenvalues are actually total energy differences. So what is approximate property in the approximate method Hartree-Fock is actually an exact property of the exact method. And this is, if you want, Koopman's theorem. So Koopmanizing a method, in a sense, means of making it Green's function oriented. So when we cast eigenvalues as total energy differences, we are actually aiming at the framework, the general and elegant framework of Green's function method, where these poles are just charged excitation, and these are the Dyson orbitals. Okay, so I don't know how much time do I have? Okay, so a few minutes where I try to discuss this theoretical statement with some numerical examples, and here we perform some Scham-Schluter solution. So we work with models here, and one-dimensional models that are quite popular to validate method. And typically you want to have a model for interacting particles. So in 1D, you have to change the shape of the Coulomb interaction. So here we use this soft Coulomb. And here we have the black potential is a double well that we treat the Hartree-Fock level. So we can solve Hartree-Fock on the double well. And we can also compute this Kohn-Sham exact exchange. So that is the local potential that minimizes the Hartree-Fock energy, or is the result of the linearized Scham-Schluter equation, this out of the Hartree-Fock self-energy. So you plug the self-energy here, you impose that the density is the same as out of a Kohn-Sham Green's function, and you obtain this equation. This is the full Scham-Schluter. Then typically you linearize it, so you put Kohn-Sham everywhere. And that is a very key result equivalent to the optimized effective potential method. So if I take Hartree-Fock, minimize it with a Green's function that comes from a local potential, that is exactly equivalent to linearizing this equation here. And this is the potential that comes out of this. So somehow it's a way to obtain also exact properties of the Kohn-Sham potential. So to understand what are the exact limits of the Kohn-Sham potential. And if you do this in Kohn-Sham, you know that you can just get one eigenvalue right, that is the topmost, the HOMO, and that's why the density decays with the exponential with the position of the HOMO with respect to the vacuum level. So somehow the HOMO needs to be exact because the density is exact, inexact Kohn-Sham. But that is the only level that is exact. So Kohn-Sham has little, as just one local potential, has little freedom. You cannot expect to obtain all exact quantities. In fact, we know that just the top eigenvalue is correct. Everything deeper is not, because we are using a very constrained potential. Then we can instead use the the spectral Chern-Schluter equation suggested by Gatti and co-workers. This is along the same lines, but uses a local dynamical potential, as I mentioned. That potential that here is solved, so these are all the potential as a function of the frequency. And in our model, we had 4 occupied states that are these highlighted in green. So you see the local potential that changes as a function of the frequency in order to describe correctly the 4 occupied states we have. And by construction, in the density of states, we obtain now that not only the HOMO is correct, but also the deeper states. And here, the counting is simple. We have 4 states. If you want, if we want to describe 4 energies, we need 4 potentials. So Koneschan is just one local potential, describes one eigenvalue, that is the HOMO. If we want to describe deeper, we need more potential. That is the meaning of this frequency dependence in the spectral function formulation. And then also by chance here, we noticed that Hartree self-interaction correction is a very good approximation to Hartree-Fock. And this is a general feature. So we can go even a bit more complicated. This is a model not based on Hartree-Fock, but on a model GW self-energy that is the black. So we have just quasi-particle states and satellites. You see every state, if you want, has its own satellite. And if we do Hartree-Fock is this part of here, no satellites. And if we do the spectral potential Chern-Schluter, of course, that by here are the potentials, and those by construction just describe the whole spectrum, including satellites. If we make a quasi-particle approximation, instead we retain only the quasi-particle peaks, and so we have a method with 4 potentials that is not able to describe satellites, but is able to describe the 4 quasi-particle peaks. And somehow this is the model for what our Koopmans construction does. So we have n electrons, n potentials. The n electrons, the n vectors are orthogonal. So we are, and they are normalized to 1. We are not aiming yet, to describe satellites, but we can describe their position in the spectrum. This is more or less it. And one last remark, and then I conclude. It is that while Koneschan exactly needs to develop some features that are somehow pathological, or if you want, are simply difficult to approximate. One, and the famous or infamous one, is the derivative discontinuity that can shows up as a sudden jump of the potential as you add a fractional electron to the system, or here a dissociation of donor-acceptor molecule shows up as this offset here. And the point is that with one Koneschan potential, when you are in the binding situation, you have just one HOMO that needs to be described exactly. When you take the 2 far apart, somehow you go into the limit where you have 2 separate objects, and there you need to have 2 exact HOMOs, but you have just one potential. And so the trick of the Koneschan potential is to develop this offset. In the middle of nowhere, where there's no charge density, you have a finite offset. It's a feature that is very difficult, likely to approximate. The good news, and okay, here there's a further analysis, but the good news is that the spectral potential doesn't have this need, because it simply as many potentials as you go. It is a collection of many potentials, so it doesn't need to have a derivative discontinuity. This is similar, if you want, to the framework of generalized Koneschan, where you have, instead of a local, a non-local Koneschan potential, well, a non-local generalized Koneschan potential, and that doesn't require, as milder requirements on derivative discontinuity. So the derivative discontinuity set is absorbed in the non-locality. Here we do the same. We do not need derivative discontinuity. That is good news for approximations. And then here is the last piece of information that is, okay, you have been talking about this spectral function that could exist. We believe it, but how difficult is it to be approximated? And here is the spectral potential compared, the exact one, compared with self-artery correction. And you see that is the dashed line self-artery. You see that you do already at the self-artery level, that is the simplest orbital density dependent approximation, you do a very good job here. And even better if you, instead of plotting the potential, you plot potential times orbital. You do here an extremely good job. So somehow I think that there are good hopes that it's not impossible to build approximation to this spectral potential. And by the way, self-artery, that is one of the ingredients of Koopmans, is already shown to do a good job in describing what the potential, the local potential coming from artery Fock. And this also is a take-home message. With the Koopmans, we have a screening factor. What we really do, I think, is to get a decent description of screened exchange. Again, there is another similarity point with DFT plus C. Okay, with this, if you want, this is a sketch of the land for theoretical framework. I think we can throw ourselves to be here. So just getting a bit out of DFT, climbing this hierarchy of spectral methods. Here it is. We would like now really to build this more formally. And with this, let me conclude. So I leave the conclusion here, but before doing that, again, let me thank all the people that got involved at different levels. So I'm pretty sure that I'm forgetting someone. Apologies, and here are the conclusions.
Thanks. Yeah, thank you very much. So I have a couple of questions regarding. So first, you mentioned that you would apply some unitary rotations to obtain different energies, but from what I've seen, the after rotation it is just the same. It is completely symmetrical. So where did I miss it? And what changes after you rotate your system when it seems to be symmetrical?
So the point is that in unitary invariant methods, like methods that depend on unitary invariant quantities, like the densities or the density metrics, like artery Fock, you apply a unitary rotation of your orbitals, and your basic quantity, the density of the density metrics, stays the same. So your total energy is simply unchanged. And in a sense, when you minimize your functional, these are zero energy modes. So you can rotate have a unitary rotation among the orbitals and energy doesn't change. And that is pretty much exploited also, for instance, in the Carparinello of quantum espresso. You minimize, and at a certain point, you can apply rotations. You have the freedom to do that, and the energy doesn't change. The point here is that the basic quantity are orbital densities. And if you rotate orbital densities, they change. Their sum doesn't, but each single orbital density changes. And so your energy in principle changes. What happens in practice, you have the zero energy mode of this rotation is now no longer zero energy. So you have a little dependency on the rotation that is on an energy scale that is different from artery, for instance, from the big pieces of the total energy, but still is there. And that leads to minimization of the total energy by orbitals that have a specific unitary rotation. Once you are there, you get this lambda matrix via the Peterson condition that is Hermitian. You can diagonalize, so you remix them. But those are these canonical orbitals, the eigenvectors, but are not those used to evaluate the energy. So the energy is minimized by a specific unitary rotation among them.
Thank you. Second issue, very fast. You mentioned you did not align the energy. When you compare the experiment, how did you calculate the, let's say, actual value of the energy? Because like, you can shift it with respect to the vacuum.
With respect to the vacuum.
And since this is all a bit new to me, and I'm trying to, get a grasp on the big picture, let's say, how would you, and you did it a bit, but how would you very briefly compare this to GW? Where do they stand?
Yeah, I think that so in a work with Nicola, we were drawing the comparison a bit formal and as far as possible, because of course it's not it's still a bit heuristic, but somehow this is a static approximation. We don't have satellites, so it looks as if we are doing an evaluation of cosec of the cosec energy of GW, perhaps with the FXC entering everywhere that can be seen as a vertex correction. So if you want, this could be seen as self-consistent cosec. And so I wanted to go here, though. Yeah. And if you want, it is where Koopmans stand. This is a theory of the local spectral density that is very similar to the local Green's function that could be seen as the theory underpinning the MFT. And here are full Green's function functionals, GW being one of them.
Thank you very much.
Yeah. Very nice. So I want to just because at the beginning we talked about other two ways of looking into it. So and here you have a functional that by construction is actually taking away this nonlinear part and adding this linear. But in the KR form, let's say we don't have these values on the correction term. So my question is would be if the deviation from this linearity is just one of the consequences of the second direction error, or those two are related?
So this is a very good question, and actually I recommend to go to that paper by Kummel and Kronik, where they really discuss that. The point is that self-interaction as a label doesn't have a single definition. If you want, self-interaction can be seen or thought as a one electron exactness, so methods that are one electron exact could be thought to be self-interaction free. That is the case of R3 Fock, for instance, or Perdue-Junger SIG. Though when you come to R3 Fock, the piecewise linearity problem is actually there, and Perdue and co-workers argued that that can be called many-body self-interaction figure. It depends also on, I think, what is convenient for you when discussing a method. In DFT, when you have many electrons, you don't have many other options to describe self-interaction. So that you know that piecewise linearity is an exact property. You can connect self-interaction to that with the reasoning we used. Okay, the dependency on the bomb on its own occupation. In diagrammatic methods, you can even think of methods coming from diagrams that have some symmetries. But you need diagrams, so that reasoning you can follow in diagrammatic methods. In DFT, you don't have much knowledge of what is inside the functional. In one electron exactness is there all the time. These are all similar, but not always the same. So I think that KI is a clear example where you fix piecewise linearity, and also is instructive because it tells that that fixing of piecewise linearity may not even percolate to the total energy, right? If you don't think that is a drawback in a perspective, is a pro is a feature in another perspective, because perhaps just allows for correcting the eigenvalues. And there is also all the reasoning about the asymptotic behavior of the Kohn-Sham potential. That is all another story that we are not treating at all.
So if I may add, so this is a very important question indeed, that there seems to be a discrepancy in correction of piecewise linearity and locality. I think it's also related to the problem of size consistency.
Oh yeah,
that is that if you break apart the system and impose p-parity to a new system, you may not get it for the united subsystem that you have. So I think one of the key words also is that issue of size consistency. That
absolutely,
yeah,
absolutely.
That I think is related to your question. We want to make this size consistent as well.
Thanks for the talk, really nice. And my question would be exactly related to this paper.
That's great.
Really nicely, really liked it. And it's regarding to the electronic band gap and why GFT kind of struggles and has no reason to complete it right. So at first you mentioned this derivative of the thermal energy with respect to the computation. We don't determine it correctly in certain direction. But then you mentioned about this delta SPF approach, which in principle one could think about it to do this calculated band gap to the energy to low energy differences. But then what I struggled to understand was there's a sentence that you mentioned that this is a kind of breakdown in the thermodynamic limit and asymptotically approach the quantum gap. And one of these problems could be also related to derivative discontinuity of the quantum potential. And then that's the point where you start getting the class, where GFT is not able, will never be able to compute the band gap correctly. And also related to the presentation that Professor Davo mentioned before, I was sort of coming to develop a question regarding then would Koopmans be as good as delta SCF because you're not actually correcting your photo energies on integer occupations. So I would tend to think that it would be as good as it. But if it kind of has inherent problems, wouldn't you go back to your constant band gap? And I mean, where is exactly where Koopmans is able to overcome these problems and still provide you better band gap?
This is an excellent question, actually. So first comment is that the band gap is not a problem of DFT. Is a problem of Kohn-Sham DFT. So DFT has total energy, you can compute total energies, and the band gap is a ground state quantity out of total energies, n minus n-1, n plus 1, minus n. And indeed you can do, and that is called delta CF. And for molecules, it works decently well, except that you have this problem of binding anonyms, if you want. That is a bit difficult. In Kohn-Sham DFT, there's another way to estimate the gap that is via the Kohn-Sham gap. Okay, so the gap is a total energy difference, but can also be evaluated out of Kohn-Sham gap. Problem is that you need to add this extra bit that is the derivative discontinuity. That is a property of Kohn-Sham. So if you, it's not a property of DFT, it's a property of Kohn-Sham, of the way you solve the problem. Again, is a problem of the theoretical framework. If you were doing generalized Kohn-Sham, actually there's a nice paper by, I think, Purdue. There are all the big names there, there's Purdue, Hardy, Gross, and so on and so forth, discussing generalized Kohn-Sham for band gaps. It's a PNAS paper, is cited in our review. They really make the point that this issue of the derivative discontinuity can be absorbed into the non-locality of the potential. The reason when you go to the infinite limit is exactly, so delta CF fails exactly because of the derivative discontinuity of that is not in approximate functionals. Okay, because when you add one electron that is infinitely diluted, you are adding locally a tiny fraction of an electron, and if your functional is just local, it just sees local and continuous, just sees a tiny bit of an electron, so you don't have derivative discontinuity. What saves the day in the Koopmans case is to work with localized orbitals. So somehow the fact that the unitary rotation of Koopmans takes you always to minimize the energy via localized orbitals, and the correction is built on these localized orbitals, keeps you in the region, in the comfort zone for your delta CF, and then you inherit the accuracy from there. I think this is going to be discussed extensively by Edward.
Questions?
So, with this, sort of going back to the question of how the relevant models is just the self-interaction equation that's present in KPZ and not in AI. So the result you put at the end, when you were sort of comparing the spectral functions, and you're comparing this partially self-interaction equation, how much of that is applicable to KPZ but not AI? So what of these sorts of negative spectral functions can you only draw if we've got this self-interaction equation? Or do you think it's just the general, we're trying to get towards general properties of only functionals?
Sorry, I'm not sure I got part of it. So,
so at the end, how much of these conclusions with this spectral connections rely on the fact that we've got a self-interaction correction as opposed to us just generally having an ODD function?
So I think that the conclusion about the flexibility of the theoretical framework, so the fact that you have multiple potentials and that in principle allows you to describe the multiple energy levels, including deeper levels, that is general. If you want, the question is whether or not your current approximations in the ODD form are really thought and are able to describe that. And we hint this from art to self-interaction and exchange self-energy, suggesting that art to self-interaction that is part of the Koopmans correction can just describe exchange. That is the big missing piece, if you want, in our approaches. But then everything is kind of a posteriori when you look at the way Koopmans results or KIPZ is, and indeed it turns out that he's able to describe deeper levels, and you understand why he can describe deeper levels, but somehow there's no theorem or argument a priori that tells that any ODD should be describing deeper levels. Actually, Perdue Unger Sig is not. So it's really, you have the flexibility, but you have to cast the physics in. I don't know if this answers the question.
If I can follow up. So in a sense, we're doing exactly what we've done for 15. Also, you know that you can do a function of your density that you can state, and so you have the chance, like you mentioned, for the spectral property, and you need to put in exact condition to the right approximate function, like they do for PV and so. And here, the exact condition you use is the condition that you said that the exact next function should have. So I was wondering, you know, if maybe the more you add exact condition, the better you define your spectral function or the approximate or the
I think it's an interesting perspective. It's a nice way to look at it. Yeah, I think that I've been asking and telling this myself many times. If we were not doing piecewise linearity, the ODD imposing piecewise linearity, we would not get accuracy on the orbital energies. That is somehow what you are saying now. Yeah, I agree.
energy drop, and this is not if we stay in a quite future. Now you show you are to talk to other frequency benefit and you start developing other peaks that you don't get. So, but in the general framework, I can add an extra frequency or an extra potential that might describe that extra peak or extra field. But now, if I can clearly see what would be the correspondence, remove an electron, so I know what are the physical for electron in the system. What would be the degrees of freedom that I might need to look at if I want to reproduce the extra features of the? I mean, it's not an electron. Right?
I think that here the picture developed by Tommaso with the algorithmic inversion somehow helps. So somehow the satellites can really be seen formally as states hybridized in a larger system. So you take your system, you put a bath, you hybridize your states with the bath, and that is a satellite. So you need to have some extra degree of freedom that interacts with your levels. So I think that a way to develop that would really be, so either adding frequencies here and there as we discussed, like in the screen coefficients, or in that perspective to just enlarge the system and do the Koopmans construction in a larger system. And then you project back to your embedded system and you get the satellites. That would be interesting, actually, because so physically the satellite would correspond to an excitation. And in GW you get an RPA excitation that so excitation from the RPA screening that is typically not very much accurate for satellites, and you need to resort to cumulant expansions and so it would be extremely interesting, I think, to be able to estimate that out of functional ingredients, DFT ingredients, in a sense.
Okay. No more questions. Let's thank Andrea again.